Let's go back. All the way back. Not to the beginning of Earth. Not to the formation of the solar system. Not even to the first stars igniting in the darkness of the early universe. Further, to the very first moments after the Big Bang. To a time so early that the word early barely applies. We're talking about the first microsecond. The first nanosecond. The first 10 to the power of -43 seconds. A number so small that it doesn't correspond to anything you've ever experienced in your life. This period is called the Planck epoch. And in this window of time, the universe was not what we think of as a universe. It was a seething, unimaginably hot plasma, a single point of pure energy, expanding at a rate that defies intuition, hotter than anything that has existed before or since. At this temperature, around 10 to the 32 degrees Kelvin, the four fundamental forces of nature were likely unified into a single force. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all one thing, all indistinguishable. The universe at this moment was a kind of perfect symmetry, and symmetry, in physics, is another word for nothing interesting happening. But then the universe cooled, and as it cooled, that symmetry broke. The forces separated from each other, one by one, like ice crystallizing out of water. Each separation released enormous amounts of energy, drove the universe to expand in new ways, and changed the rules of what was possible inside it. And here is where the story of matter begins. As the universe cooled past certain thresholds, something extraordinary happened. Out of pure energy, out of nothing but the quantum vibrations of the early cosmos, particles began to appear. Matter flickered into existence. But it never came alone. This is one of the most fundamental rules of physics. Every time a particle of matter is created from energy, an equal and opposite particle of antimatter is created alongside it. Always in pairs, always perfectly balanced, always together, an electron appears, and immediately a positron. A quark materializes, and with it, an antiquark. Matter and antimatter born simultaneously, mirror images of each other in every way except one. Their charge is reversed. And when they meet, when matter touches antimatter, they do not coexist, they annihilate. They convert back into pure energy, perfectly and completely, leaving nothing behind. So here is the problem. In the first fraction of a second after the Big Bang, the universe created matter and antimatter in equal amounts. Then that matter and antimatter found each other. They collided. They annihilated. They converted back to energy. Every particle of matter was matched and destroyed by a corresponding particle of antimatter. The math says, the result should be a universe of pure energy, pure light, zero matter. An endless, empty, featureless sea of photons traveling through nothingness forever. No galaxies, no stars, no carbon, no DNA, no observers. Nothing that could ever look up and wonder where it came from, and yet here we are, which means something went wrong. Or rather, something went asymmetrically right. Somewhere in the first second of the universe's existence, the balance was broken. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. A tiny excess. A fraction of a fraction. An imperfection so small that it seems almost negligible. But it wasn't negligible. That one extra particle of matter per billion, that tiny, almost non-existent imbalance, is the reason everything exists. The matter and antimatter annihilated each other as predicted. All of it, every matched pair. And what remained, what survived the annihilation was that small surplus, that leftover, that rounding error in the math of the early universe. That is you, that is the Earth, that is the Milky Way, that is every star you've ever seen or imagined. All of it descended from a tiny excess of matter that, by rights, should not have existed. And physicists cannot tell you why that excess existed. They have a name for the process, baryogenesis. They have conditions that must have been met, first laid out by Soviet physicist Andrei Sakharov in 1967, known today as the Sakharov conditions. But they don't have a mechanism. They don't have a complete, verified, experimentally confirmed explanation for how or why matter came to dominate antimatter in the early universe. This is not a small gap. This is not a minor footnote in an otherwise complete theory. This is a hole in the foundation of everything. In 1967, a man named Andrei Sakharov did something remarkable. Sakharov was a Soviet physicist, brilliant, decorated, the father of the Soviet hydrogen bomb. But by 1967, he had become something else too, a dissident, a man who was increasingly willing to say uncomfortable things out loud. And the uncomfortable thing he said in 1967 was this: if the universe began in a state of perfect symmetry between matter and antimatter, then for matter to dominate today, 3 specific conditions must have been violated at some point in the early universe. He called them conditions, but they might as well be called requirements for existence. The first condition is that there must have been some process in the early universe that violated what physicists call baryon number. Baryon number is essentially the count of matter particles minus antimatter particles in a system. In normal physics, this number is conserved, it doesn't change. But Sakharov argued that for matter to win, that conservation must have been broken. Some process must have created more matter than antimatter, even briefly, even slightly. The second condition is that the symmetry between matter and antimatter, a symmetry called CP symmetry, must have been violated. CP symmetry is the mathematical rule that says the laws of physics should be identical whether you're looking at a particle or its antimatter mirror image. If CP symmetry were perfect, any process that favored matter would be exactly cancelled by an equal process favoring antimatter. So for an asymmetry to develop, CP symmetry must be broken. And here's the thing, we know CP symmetry is broken. We've seen it in experiments. The decay of certain particles, kaons, B mesons, does not proceed identically for matter and antimatter. The asymmetry is real. The universe does treat matter and antimatter slightly differently. But, and this is critical, the amount of CP violation we've measured in the standard model of particle physics is nowhere near large enough to explain the amount of matter that exists today. The observed asymmetry is too small by a factor of roughly 10 billion, which means there is CP violation we haven't found yet. Physics we haven't discovered. A deeper asymmetry in the laws of nature that we are, as of today, completely blind to. The third Sakharov condition is that the universe must have passed through a period of thermodynamic non-equilibrium, a state where things were happening faster than the universe could stabilize them, creating the conditions for an asymmetry to lock in rather than be smoothed away. These 3 conditions are all probably met, in one form or another. But the details, the actual mechanism, the actual physics that broke the symmetry, remains unknown. And this is where things get philosophically vertiginous, because it's not just that we don't know the mechanism. It's that every time we find a new piece of the puzzle, every time the Large Hadron Collider fires up and smashes protons together, and we analyze the debris, we keep finding something frustrating. The standard model works. It works beautifully. It predicts the behavior of particles to more decimal places of accuracy than any other theory in the history of science. It is arguably the most successful scientific theory ever constructed. And it's not enough. It cannot explain why we exist. Let's zoom out now. Let's pull back from the subatomic world of quarks and bosons and look at the universe as a whole. Because the matter-antimatter problem, as deep as it is actually just one layer of the mystery. There's another layer. And it might be even stranger. It's called the fine-tuning problem. And when you first encounter it, it sounds almost religious. It sounds like an argument for a designer, a creator, an intelligence behind the cosmos. Physicists are deeply uncomfortable with it for exactly this reason. But the numbers are real. And the numbers are extraordinary. Start with the cosmological constant. The cosmological constant, the symbol in Einstein's equations, represents the energy density of empty space, what physicists call vacuum energy, the energy that exists in a perfect vacuum, in absolute nothingness. And quantum mechanics predicts that this value should be enormous, because empty space is not actually empty. It's seething with quantum fluctuations, with virtual particles constantly popping in and out of existence. The predicted value of the cosmological constant, based on quantum field theory, is somewhere around 10 to the power of 120 times larger than the value we actually observe. That is not a small discrepancy. That is a discrepancy of a factor of 1 followed by 120 zeros. It is the largest discrepancy between a theoretical prediction and an experimental observation in the history of science. Physicists call it the worst prediction in physics. Some call it the vacuum catastrophe. And here's why it matters. If the cosmological constant were even slightly larger than it is, not a factor of 10 to the 120, but even a modest deviation from its observed value, the universe would have expanded so rapidly after the Big Bang that matter could never have clumped together. No galaxies, no stars, no planets, nothing. If it were slightly smaller, slightly negative, the universe would have collapsed back in on itself almost immediately. A big crunch before the universe ever had a chance to develop complexity. The cosmological constant sits in a narrow window, an almost impossibly narrow window, that permits the existence of structure, of complexity, of us. And we don't know why. Now consider gravity. The strength of gravity, the gravitational constant g, determines how strongly matter attracts other matter. If gravity were significantly stronger, stars would burn through their fuel in thousands of years rather than billions, far too quickly for complex chemistry and life to develop. If gravity were significantly weaker, gas clouds would never collapse into stars at all, and the universe would be dark and cold forever. The gravitational constant sits at a value that permits stars to burn for billions of years, long enough for planetary systems to form, for chemistry to become complex, for evolution to occur. Consider the strong nuclear force, the force that holds atomic nuclei together. If it were a few percent stronger, all the hydrogen in the early universe would have fused into helium before stars ever formed. No hydrogen means no water. No water means no chemistry as we know it. If it were a few percent weaker, nuclei couldn't hold together at all. No atoms beyond hydrogen. No periodic table. No complexity. Consider the ratio of the electromagnetic force to the gravitational force. This ratio is approximately 10 to the 36, an enormous number, but it needs to be roughly that large. If it were different by a significant amount, the balance between the forces that allows stable atoms and stable planetary orbits would collapse. Consider the number of spatial dimensions. Physics as we know it, with inverse square laws for gravity and electromagnetism, only works in exactly 3 dimensions of space. In 4 spatial dimensions, orbits would be unstable. Planets would spiral into stars. Atoms wouldn't hold together. In 2 dimensions, the complexity necessary for biology couldn't exist. You can go down this list indefinitely. The mass of the electron, the mass difference between the proton and neutron, the value of Planck's constant, the speed of light. Every fundamental constant, every law of physics, sits at a value that makes complexity possible, and in most cases, sits at a value that is extraordinarily suspiciously, almost impossibly precise. Physicists call this the fine-tuning problem, and it comes with a question attached. A question that is either very simple or infinitely deep depending on how long you think about it. Why? There are, broadly speaking, 3 doors physicists and philosophers have proposed as answers to the fine-tuning problem, and none of them are comfortable. The first door is, it's a coincidence, the universe just happens to have these values. There's no deeper reason, no explanation. It's a brute fact of reality, like asking why there are 3 spatial dimensions rather than 4. There isn't an answer, that's just how it is. Physicists call this the shut up and calculate approach. The universe is what it is. Our job is to measure it, not explain it. This is philosophically unsatisfying to almost everyone who encounters it. It feels like giving up. It feels like saying the map ends here and refusing to look further. But it might be true. Some things in nature may simply be contingent. They are the way they are. And there is no deeper why. The second door is a multiverse. This is, by far, the most popular answer among theoretical physicists today. And the logic is seductive. If our universe is not the only universe, if there are a vast, perhaps infinite number of universes, each with different values of the fundamental constants, then the fine-tuning problem dissolves. Most universes have values that don't permit complexity. They're dark, featureless, short-lived, or structureless. But in an infinite landscape of possibilities, some universes will by chance have the right values. And observers, creatures complex enough to ask the question, can only exist in those universes. This is called the anthropic principle. And it's not entirely circular reasoning. It's making a real prediction that we should find ourselves in a universe whose constants permit our existence. Because in all the universes where they don't, there's no one to notice. The multiverse is appealing. It solves the fine-tuning problem without requiring a designer. It fits naturally with certain versions of inflationary cosmology, which predict that the Big Bang-like event that created our universe was not unique, that space itself continually spawns new pocket universes, each with potentially different physical laws. But here's the problem with the multiverse. It's not falsifiable. We cannot see other universes. We cannot measure them. We cannot test the hypothesis. Other universes, by definition, do not interact with ours in any measurable way. The multiverse is consistent with everything we observe, precisely because it makes no predictions we can check. It is, some critics argue, not science in the traditional sense. It is a metaphysical hypothesis wearing a lab coat. The third door is the one physicists are most reluctant to open. What if the constants aren't arbitrary? What if there is a deeper theory, one we haven't found yet, that derives the values of the fundamental constants from first principles? What if, when we finally understand physics at the deepest level, we'll find that these values couldn't be any other way? That a universe with different constants is not just unlikely, it's mathematically impossible. This is the hope, the dream. The reason string theory and M-theory and loop quantum gravity and a dozen other approaches continue to attract brilliant minds despite decades of not producing testable predictions. If there is a final theory, a theory of everything, maybe it will tell us not just how the universe works, but why it couldn't work any other way. Maybe the fine-tuning will turn out not to be fine-tuning at all, but necessity, mathematical inevitability. The universe not chosen from a menu of options, but the only possible solution to the deepest equation. Nobody has found this theory yet, and there's no guarantee it exists. We've talked about matter and antimatter. We've talked about fine-tuning. We've talked about multiverses and final theories. But there's a deeper question that all of this circles around. A question so stark that most scientists avoid framing it directly. Why is there something rather than nothing? Not why does the universe have these constants? Not why did matter win over antimatter? But the most primitive, fundamental question possible. Why does anything exist at all? The philosopher Gottfried Leibniz asked it in 1714. 300 years of philosophy and physics have not produced a consensus answer. Some physicists argue that the question is malformed, that nothing is not a stable state, that quantum mechanics actually forbids true nothingness, that a perfect vacuum is inherently unstable, and will always fluctuate into something. Stephen Hawking and Leonard Mlodinow argued in their book The Grand Design that the universe could have arisen from nothing through the laws of quantum gravity, spontaneous creation, no cause required. But this answer always runs into the same problem. Where did the laws of quantum gravity come from? If you say, the universe came from nothing via quantum mechanics, someone will always ask, why is there quantum mechanics? Why are there laws at all? Why is there mathematics that describes physical reality? Why does reality obey rules? Every attempt to answer, why is there something rather than nothing, seems to push the question back one level, not eliminate it. Maybe the laws themselves are necessary. Maybe mathematics exists independently of physical reality, and physical reality is in some sense made of mathematics. This is the view of physicist Max Tegmark, who argues that every mathematically consistent structure exists as a physical reality somewhere in the multiverse, and we find ourselves in one because we must be somewhere. But then, why does mathematics exist? Why is there logical consistency, rather than pure chaos? The philosopher David Hume argued that we cannot reason our way to an explanation for existence, because existence is the precondition for reason itself. You cannot step outside of everything that exists and ask why it exists from a vantage point of pure nothingness. You're always inside the thing you're trying to explain. This is not a failure of imagination. This is a structural problem with the question itself. And yet, and this is what keeps physicists and philosophers and curious humans up at night, the question doesn't go away. It feels like it should have an answer. The universe's existence feels like it requires explanation in a way that its non-existence wouldn't. Nothing requires no explanation. Something does. That asymmetry in how we think about existence and non-existence might itself be a clue, or it might be a cognitive bias, the result of minds that evolved to find causes for things, struggling to accept that the most fundamental thing of all might have no cause. This is not purely theoretical. Right now, in the present, experiments are running that are trying to crack the matter-antimatter mystery specifically. The most powerful of these is at CERN, in Geneva, Switzerland. The Large Hadron Collider, the largest most complex scientific instrument ever built, smashes protons together at energies approaching the conditions of the early universe and looks at the debris. One of its primary missions is to find new physics beyond the standard model, new particles, new forces, new symmetry violations that could explain baryogenesis. So far, despite years of operation and petabytes of data, it has found exactly one new particle, the Higgs boson, discovered in 2012. The Higgs was predicted by the standard model, so its discovery was a triumph, but a conservative one. It confirmed what physicists already expected. It did not open the new door that many hoped for. There is also an experiment called BASE, the baryon-antibaryon symmetry experiment, which traps individual antiprotons and compares their properties to protons with extraordinary precision. If there's any difference, any tiny asymmetry in how the two particles behave, it would be a crack, the standard model, and a potential clue to baryogenesis. So far, no difference found. The proton and antiproton appear to be perfect mirror images of each other, to the limits of measurement. At the T2K experiment in Japan, physicists are firing beams of neutrinos and antineutrinos across the country and measuring how they oscillate between different types. Neutrinos are ghostly, almost massless particles that pass through matter almost without interaction, and they have a strange property. They can spontaneously transform into different types as they travel. Physicists hope that matter neutrinos and antimatter neutrinos oscillate differently, another form of CP violation that could help explain the matter surplus. In 2020, T2K released results suggesting a significant difference in how neutrinos and antineutrinos oscillate. It was a tantalizing hint, but the statistical significance wasn't enough to make a definitive claim. More data is needed, and this is the rhythm of the field. Hints, suggestion, results that require confirmation. The universe teasing physicists with the possibility of an answer without quite delivering one. Meanwhile, the cosmological constant problem sits there, unsolved, a factor of 10 to the 120, staring back at every theoretical physicist who tries to calculate the vacuum energy from first principles. Supersymmetry, a theoretical framework that many physicists hoped would solve multiple problems at once, including fine-tuning, has not shown up in collider data despite extensive searching. Extra dimensions predicted by string theory have not been observed. Dark matter, which makes up roughly 27% of the universe's mass energy content, has not been directly detected despite decades of experiments. We are, in a very real sense, in the middle of a crisis in fundamental physics. The standard model works, but it's incomplete, and the incompleteness is not in some obscure corner. It's at the very heart of the biggest question: why does matter exist? Richard Feynman was once asked a version of this question. Not the cosmological constants version, but the deeper version. The why is there something rather than nothing version. And Feynman, characteristically, did not give a comfortable answer. He said something like this: I think it is much more interesting to live not knowing than to have answers which might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything. He was talking about a general philosophy of science. But it applies here with unusual force, because the honest answer to why does the universe exist is, we don't know, not we're close to knowing, not the answer is probably X. Genuinely, honestly, fundamentally, we do not know, and the tools we would need to answer the question may not yet exist, may not yet have been invented, may require a revolution in physics as fundamental as the one Einstein started with relativity, and Bohr started with quantum mechanics. But here's the other thing Feynman understood, the thing that makes this not just depressing, but genuinely exciting. The questions we can't answer are the most interesting ones. The fact that physics cannot explain why the universe exists is not a failure of science. It's a frontier. It's a door that is still closed, with the most extraordinary thing imaginable on the other side. Think about what an answer would mean. If we understood why matter and antimatter are asymmetric, if we found the mechanism of baryogenesis, we would understand something about the laws of physics deeper than anything in the standard model. We would understand why we exist in a physical, literal, scientific sense. If we solved the fine-tuning problem, if we found the final theory or confirmed the multiverse, or discovered that the constants are mathematically necessary, we would understand the nature of physical law itself, why there are rules, where they come from, whether they are contingent or necessary, whether our universe is the only possible universe or one of countless alternatives. If we answered the deepest question, why is there something rather than nothing, we would understand existence at the most fundamental level possible. We would have completed a project that Leibniz and Aristotle and Newton and Einstein and Feynman were all working on, in different ways, across centuries. That would be the greatest scientific achievement in the history of human civilization. And it hasn't happened yet. There's one last thing I want to leave you with. Remember that tiny excess of matter. That one extra particle per billion. The rounding error that survived the annihilation of the early universe and became everything. That is you, not metaphorically, literally. The atoms in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, are descended from those survivors. From that improbable, unexplained tiny asymmetry that tipped the scales in favor of existence over nothingness. You are not a background feature of the universe. You are not an inevitable byproduct of physical laws grinding forward mechanically. You are, in a very deep sense, an accident, a remainder, a consequence of a mystery that the most brilliant minds in human history have not been able to solve. And you are here, right now, asking questions about it. That's extraordinary. Not in a vague motivational poster sense, in a precise, literal, scientific sense. The universe produced beings capable of wondering why they exist, out of the very asymmetry whose explanation we don't have. The rounding error became self-aware. The leftover started asking questions about the original equation. Richard Feynman said that nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. Pull on any thread far enough, and you find everything connected to everything else. The thread we've been pulling today, why does matter exist, leads to the Big Bang, to quantum mechanics, to the structure of space-time, to the nature of physical law, to the deepest question in metaphysics. We don't have the answer, but we have the question. We have the mathematics. We have the experiments running right now, at this moment, probing the structure of reality at energies and precisions that would have seemed like mag to scientists a century ago. And we have this. The stubborn, unreasonable human insistence on asking why. The universe shouldn't exist. Physics can't explain why it does. And somehow, impossibly, here we are, children of the asymmetry, asking the universe to explain itself. Maybe that's enough for now. Maybe that's everything.